We had a section earlier in this chapter, I believe it was section 4, when it was nice to know these patterns, so you could kind of go straight from like a FOIL type problem to the answer instantly, and it wasn't very important that you know it. In this section, we're again working with those special patterns. There are several of them, however, there's only one that you really want to know, like for sure, because otherwise you won't be able to factor it very easily. Okay, so factor perfect square trinomials and the difference of squares, and then we're going to use patterns to factor those special cases. Once you get the hang of those special cases, it becomes pretty easy. However, I want to make sure that you understand that not all problems are special cases. So what we're doing in this section does not apply always, only to special cases. So let's simplify this. What do we need to do to simplify a plus b squared? Right, remember this is a FOIL problem. This is a plus b times itself. And now we're going to FOIL that, and when we FOIL it, we get what? So AB again, right, plus b squared. And then you combine like terms and you get a squared plus 2ab plus b squared. On the right side, we have a minus b squared this time. What do we do here? Yes, it's still a FOIL problem, a minus b times a minus b. Remember to write those out like that. Now we FOIL this one and we get a squared minus ab plus b squared. Combine like terms and you have a squared minus 2ab plus b squared. Notice that everything we had up here is repeated down here. Everything we had up here is repeated down here. This was section 4. Today what we're going to do is we're going to go backwards. We're going to go backwards. And it's helpful to know this pattern to go backwards. If you don't know the pattern, you can still go backwards without doing that pattern. You can just factor it like we've been doing, and you'll wind up with this case in the end anyway. Okay, so this is another one that you don't necessarily have to know. These guys right here, this one and this one, are called perfect square trinomials. They're called perfect square trinomials because, first of all, how many terms do they have? 3. So that's the trinomial part. The second part is, if you notice, is a squared a perfect square? Yes. Is b squared a perfect square? Yes. And what the way we got this is by taking something and squaring it. So that's where the perfect square comes from. In this case, the only difference between this answer and this answer is the fact that we have this minus sign sitting right here in the middle term. The minus sign right here comes from the fact that we have a minus sign right there. This here is a plus sign, so that comes from the plus sign right there. And the second term here, or the third term, sorry, is always positive. So let's go on. And here's your key concept for this section. If you're trying to factor perfect square trinomials, and you recognize that it's a perfect square trinomial, then basically what's going to happen is if you see a perfect square in the first term, and you see a perfect square in the last term, you may have a perfect square trinomial. You have to check, though, to see if the middle term matches the pattern. So what you're going to do is find the square root of this guy, or in other words, what number times itself gives you this. Find the square root of this guy, or again, in other words, find that what number times itself gives you this. And then this middle term says multiply those two results together and then double it. And if you get exactly your trinomial, then you can factor it quickly into that case, which then turns into that case right there. What we would start with if we were going the other way. If you have a negative sign sitting there, the same result is true, except now it's minus and minus, and then you would wind up with that as your answer. So for example, x squared plus 8x plus 16. Is x squared a perfect square? Yeah, x times x is x squared. So therefore, the square root of x squared is x. Is 16 a perfect square? Yeah, what number times itself gives you 16? Yeah, 4 times itself gives you 16. Now, if I multiply these two numbers together, what do I get? What's 4 times x? Just 4x. And now the pattern here says double that. What do I get when I double 4x? I'm just multiplying 4x times 2. What do I get? 8x. Is that the middle term here in this problem? Yeah, it is. So after I go through that whole process, I can say, okay, this is a perfect square trinomial, so I can break this thing into x plus 4 times x plus 4, and then write my answer as x plus 4 squared. Or basically, just go to this form. I have a plus sign sitting here, so I put a plus sign there. And then I take that number, x, and I take that number, 4, and I'm done. The other example, 4n squared minus 12n plus 9. Check to see if it's a perfect square trinomial. If it is, then we can use this pattern. Is 4n squared a perfect square? Is there a number times itself that gives you 4n squared? 2n times 2n is 4n squared. So yes, this is a perfect square. Is 9 a perfect square? Yes. What number times itself gives you 9? 3. So now I have 2n sitting here and 3 sitting here. If I multiply those two together, what do I get? 6n. If I double that answer, what do I get? I get 12n, and that's the middle term. So that means that I can write my answer as something squared. The sign here is going to be the sign here. And then this number goes here, the 2n, and then this number goes here, the minus 3. And that's the answer. So that's the pattern. Again, if you don't remember the pattern, if you can't figure out the pattern, if you don't understand the pattern here, you don't have to use it. It doesn't always work anyway, so it's not a big deal. You could easily, just as easily, factor these things the way that we know how to do that already. You could use the box method on this one. You can find two numbers that multiply to give you 16 and add to give you 8 on this one. Those two numbers are obviously 4 and 4 anyway, so that's actually an easy problem. All right, on these notes I have the steps that you should probably take a look at to see if it is a perfect square trinomial. If it is, then great, you can use the pattern. If it's not, or if you can't figure it out, then just factor it the way we've been doing all along, and you'll get to the same answer anyway. So check to see if the first term and last term are perfect squares. Is 16x squared a perfect square? Yeah, what's the square root of 16x squared? 4x. The number times itself that gives me 16x squared is 4. 4 times 4 is 16. X times x is x squared. Is 9 a perfect square? Yes. The square root of 9 is 3. Now, if they are, check to see if the second term is 2 times the square roots of the first and last term. So the square roots of the first and last terms are sitting here. Now if I multiply those together, 4x times 3 is what? 12x. And if I double it, do I get 24x? Yeah. So is this a perfect square trinomial? Yes. So I can write it like one. 4x goes here, the 3 goes here, and then this sign goes right there, plus. 4x plus 3 in parentheses squared is the answer. Okay? Notice that we didn't have to look for a GCF. We didn't have to try to figure out two numbers that multiply and add. We didn't have to find AC. We didn't have to use the box method. This is a perfect square trinomial, so in one step, basically, we got the answer. And that's where that pattern becomes useful. It's not always going to work, but when it does, it's really nice. So on the second problem, 9x squared minus 6x plus 4, what should we do first? Is 9x squared a perfect square? Yes, it is. The square root would be 3x. Is 4 a perfect square? Yes, the square root of that would be 2. Now what do we do? So multiply them together and we get 6x, and then what? Double it and we get 12x. Is 12x the middle term? No. So is this a perfect square trinomial? No, this one does not fit the pattern. Okay, so that means we can't use the pattern on this one. So we'll have to factor it some other way. How would we have to factor this one? Box method. So we're going to have to do what? First look for a GCF. Is there a GCF here other than 1? No. So now we're going to do AC, which is 36. All right, now what? Okay, two numbers that multiply to give me 36, but add to give me negative 6. These two numbers are going to multiply to give me a positive, and then they're going to add to give me a negative, which means both numbers have to be what? Both numbers have to be negative. So can we think of two numbers that are both negative that are going to multiply to give me positive 36 but add to give me negative 6? Not 12 and 3. Not 9 and 4. Not 6 and 6. 2 and 18. No, those don't add to give me negative 6. Can't do it. There are no two numbers that do that. So therefore, this one can't be factored. And that's your answer right there. Yep, this is it. Some books would say this is prime. Or some books would say can't be factored. Or some books would say it's already factored. Or some books would say this is your answer. Okay? All of those would work in this case. All right, try the last one. Okay, for the third one, I'm looking at this 9 and this 16, and I really don't want to do A times C. I really don't want to do the box method because 9 times 16 is a big number. I can't even do that in my head. It's way too big. So let's check to see if this pattern works, and maybe it does, and if it does, then I can just write my answer as a perfect square. Okay? So is 9y squared a perfect square? Yeah, and the square root of it is 3y. Is 16 a perfect square? Yes, and the square root of it is 4. Okay? So basically, when you're doing these problems, look to see if you have perfect squares sitting here and here. 9 and 16 are perfect squares. That's usually a clue that it's going to be a perfect square trinomial. Now what do we do with this 3y and 4? Multiply them together. We get 3 times 4 is 12y. And then what do we do to that? So double it, and we get, and is that the middle term? Yes, so 24y is the middle term, which means that this fits the pattern. So I can write parentheses squared. My sign in between will be what? Plus, because this is a plus. And what will I write here? 3y. And what will I write here? The 4. And that's the answer. Way easier than box method on this case. As long as it works, go for it. In section 4, we also took a look at a problem that looked like this. When we FOILed this, something special happened. X times x was x squared. X times negative a is negative ax. A times x is positive ax. And then a times negative a is negative ax squared. Sorry, negative a squared. The negative ax and the positive ax add to be 0 here, so the middle two terms sort of disappear, and you're just left with x squared minus a squared. The nice thing about this is if you have a perfect square here and a perfect square here and you're subtracting them, you can go straight to that factored form right there without even really much thought. And this one pops up all the time, and this is the one that I was saying you need to know the pattern for this one. The other ones you don't need to know the pattern at all. But this one you do, and this one pops up all the time. Okay, so be watching for a binomial that's a perfect square minus another perfect square. If it is, then you can use this property. So this is called the difference of squares. Because both terms are perfect squares and there's a minus sign between them. Difference means subtract. Minus means subtract, so difference means a minus sign. Okay? When you see two terms that are perfect squares with a minus sign in between them, factor them like the above equation. Starting with this is what you'll be given. You're going to go straight to that. Okay? To get this number, you'll have to take the square root of this guy. To get this number, you'll have to take the square root of this guy. All right? And then the same thing will repeat there and there. Notice that there's a plus sign and a minus sign in each factor. All right. So steps for factoring, look for a GCF if there is one. As usual, that's always step 1. Look for a difference of squares. If you only have two terms, you might have a difference of squares. Factor the polynomial using other methods if you don't have a difference of squares. So, first of all, factor this guy. Do we have a GCF here? There is no GCF. Is 16x squared a perfect square? Is 9a squared a perfect square? Yes. Are we subtracting these two things? Yes. So we actually have the difference of two squares sitting here, which means I can write parentheses, parentheses. I can put a plus sign here and a minus sign here. And then all I have to do is figure out what the square root of 16x squared is. What is the square root of 16x squared? 4x. So 4x goes here, and 4x also goes here. And then what's the square root of 9a squared? 3a. So that means 3a goes here, and 3a goes here. And you're done. So this pattern is extremely powerful because you can make this factoring happen very, very quickly. If you don't remember the pattern, you're in a lot of trouble on this one. Take a look at the second one, 121 minus 4b squared. How many terms are there here? 2, so this could be a difference of squares. Is 121 a perfect square? Yeah. What's the number times itself it gives you? Good. And then is 4b squared a perfect square? 2b. So this is the difference of two squares because I'm subtracting them. So I can write two groups of parentheses, so with a plus and a minus. And what will I put here? 11, and here? The 2b. And then here? 11, and here? The 2b. And that's your answer. On this third one here, what do we do? It's not a perfect square, but what's the first thing we're supposed to do? A GCF. Is there a GCF here? Yeah, 3 is just 3? 3G actually is the GCF. So I'm going to write 3G, and then parentheses, what's left over? 9G squared. Good. Minus, I divided 3G by 3G and I got, it's never going to be 0 when you're factoring. 1. We started with 2 terms. We still have 2 terms in the parentheses. Okay? Now inside here, does this factor? Take a look. How many terms are here? 2. We're subtracting them, right? So this pattern could be there. Is this a perfect square? Is this a perfect square? Is there a number times itself that gives you 1? 1 times 1 is 1. So is this the difference of 2 squares? Yeah, so we can factor it. We still have the GCF out front, 3G, but then this thing turns into my 2 groups of parentheses with a plus and a minus. 3G plus 1, 3G minus 1. That's correct. Stop. So now this is the answer. Keep in mind that you have to do GCF first, and then from then, once you get that GCF out of there, you can still potentially factor what's left over. And that, in this case, that's what happened. We still had to factor it. See if we can do the last one. So what should we be thinking as we try to do this last problem here? GCF. Is there a GCF here besides 1? Nope. Okay, so now what? Are they both perfect squares? And also, what else has to be happening here? Yeah, we have to be subtracting. So, is 81 a perfect square? Yeah, what times itself gives you 81? 9. And is c squared a perfect square? Yep. And are we subtracting the 2? Yep, so the pattern fits. So I can write, what? Yep. There you go. That's the answer. Okay, last 3 problems here. Sometimes you're going to have to factor more than once. So if something factors, you might have to factor it again. And then you're not going to be done factoring until all the factoring is done. So a good example of that is this one, b to the 4th minus 16. Notice we only have 2 terms sitting here, and we are subtracting them. So maybe we have a difference of squares. Is b to the 4th a perfect square? Yeah, what times itself gives you b to the 4th? b squared does. And is 16 a perfect square? Yeah, what times itself gives you 16? 4. So we can split this, since we're subtracting these 2 perfect squares, we can split this into 2, and we'll have a plus and a minus, and what will go in the first spot? B squared plus 4, and then B squared minus 4. Okay, now, the question is, does this thing right here factor? This is a perfect square, right? B squared is a perfect square. 4 is a perfect square. Are we subtracting these 2? No, we're not. This is a plus sign here. So we don't know how to factor that. In fact, we can't factor this. So this stays the same. However, b squared minus 4, can we factor this one? Yes, we can. So the b squared plus 4 stays the way it is, and then the b squared minus 4 splits into what? Yes? Very good. That's the answer. Nope, doesn't matter. If you wrote that in different order at this point, I wouldn't mind too much. You'd still be correct. Okay, second one. Is 625 a perfect square? It's kind of a big one, but what number times itself gives you 625? 25 times 25 is 625. And then an x to the fourth, is that a perfect square? And are we subtracting them? Yep. So we can split this, and I don't have room in there, so I'm going to write it here, into what? Good. Now, does 25 plus x squared factor? No. Does 25 minus x squared factor? Yes. So I'm going to write 25 plus x squared, because that doesn't factor. But then 25 minus x squared does. What do I get? Okay, 5 minus x, 5 plus x. And now you're done. Go ahead on the last one. Do we have a difference of squares here? Yes. So this turns into? Okay. Is this a difference of squares? No. So that's why we can't factor. It doesn't fit the pattern. So y squared plus 1 sticks around. And does this factor? Y minus 1, y plus 1. Or y plus 1 times y minus 1. Either way. But that's the answer.